All right, so this is for Unit 13, which is inverse trig. And this topic is composites with inverse trig functions. And we want to add and a trig function. So it's going to be a composition of one inverse trig function and a trig function. So because we have two different types of functions for a composite, there could be two scenarios. So going back to what we talked about in Algebra 2, say that we have f of x and g of x, and they are both functions. This means there are two possibilities for composite functions. We could have f of g of x, where f is the outer function and g is the inner function, or we could have g of f of x, where g is the outer function and f is the inner function. So if we think of f as our, let's think of f as our trig function or non-inverse trig function, then the first scenario could be a trig function as the outer function, which means the inner function would be the inverse trig function. Whenever you run into this scenario, it might require a triangle. And essentially what this means is that we're able to use what's provided as the input for the inverse trig in order to construct a triangle. Because if you recall, the input for inverse trig is going to be a coordinate on the unit circle. So it could either be an x, it could be a y, or it could be a combination of the two, depending on what we're looking at as our inverse trig expression, okay? Now, the output for inverse trig is going to be an angle, or theta. So if we think of our non-inverse trig functions like cosine, sine, cotangent, tangent, cosecant, and secant, their outputs are going to be these coordinates, and their inputs are going to be the angles. So when we deal with the inverse, those two roles are going to switch. So now the input for my inverse trig are the angles, and my output will be the angles. So what I tell people is, if we think of our unit circle, what we first learned was that we would focus on our theta, and then we work our way out to find out what is that coordinate. For inverse trig, we do the opposite. We found out what the coordinate is, x, y, or any combination, and we work our way in to figure out what theta is. This is always how inverse works. The inputs and outputs will switch roles. So instead of working our way from the inside out, we work our way from the outside in. So the second scenario is going to be, we will have the inverse trig on the outside, and then our inner function will be the non-inverse trig. This one you can just evaluate. Because you're going to be given your angle as your input for this. So say that we have inverse cosine of sine of pi over 3. Because you can't construct a triangle just from the angle. Okay, yes you can, but you don't need to, because we are able to figure out what the output for this is. The output will be a coordinate point, which will satisfy as the input for that outer function, okay? So if we have sine of pi over 3, this is just a normal trig expression. I'm going to be in quadrant 1, and I want the y coordinate. So again, for compositions, you solve the inside first, and then you work your way out. So for sine of pi over 3, that is going to be root 3 over 2. So now root 3 over 2 is a standard point on the unit circle, but then also remember that there are two values that could work for cosine. It could be here, or it could be here. But now that we're dealing with arc cosine, we can only be in quadrants 1 and 2. So that means it will be this one up here, which means arc cosine of root 3 over 2 is equal to pi over 6. So no triangle was required. So what happens when you are in that first scenario? Well, the first step is if the inner expression cannot be evaluated, set it equal to theta. So that means when it can't be evaluated, that means it's not a standard coordinate on the unit circle, all right? So the output for inverse trig is theta, okay, which means the input is going to be coordinate points. So if I think of tangent, SOHCAHTOA, tangent is equal to opposite over adjacent. So that means this 8 is the opposite, and this 5 is the adjacent. And then we'll talk about that negative in a second. Now, because this cannot be evaluated, we will set it equal to theta. And when this happens, we're able to rewrite it as a normal trig expression. So what we did to get to this step is that we took the tangent of both sides. So if I take the tangent of the left side, that means I need to take the tangent of the right side. Now, tangent and arctangent are inverses, so they will cancel out, which means we're left with tan theta is equal to negative 8 over 5. And what this tells me is the sides of the triangle that I will be constructing, because now I see that I have the opposite over the adjacent. Now, this is negative. Tangent is negative in 2 quadrants, okay? It's negative in quadrant 2, and it's negative in quadrant 4. But even though we're working with tangent right now, we have to think back, what is our inverse trig expression from the start? It is arctangent. And arctangent only exists in quadrants 1 and 4, okay? So that means because it's negative, we have to be in quadrant 4. So that's the quadrant that the triangle will be constructed in. And what we can do here is, once we have this triangle constructed, and with the negative, I now know that it will be the 8 because we are in quadrant 4. This coordinate is 5, negative 8. So I know that even though the whole ratio is negative, the negative is unique to the 8, okay? Now, you're going to have to find your other side of your triangle. This is where your Pythagorean theorem will come in. A squared plus B squared equals C squared. Doesn't matter what A or B is for 5 and 8, but we end up with 5 squared plus 8 squared. The negative is insignificant. And then we end up with the square root of 89 is equal to C. Now, when you take the square root, you do get plus or minus. We can't forget that. But because we're dealing with a side of a triangle, specifically the hypotenuse in this case, it is always going to be positive, okay? So once you have your triangle constructed, you have a setup for theta, which is what we needed, okay? So once we find out what that triangle looks like, we have a triangle for theta. So I would work my way out to the next part, which would be sine theta. Sine is going to be opposite over hypotenuse. And if I look at the triangle that I constructed from arctangent, opposite is negative 8, hypotenuse is root 89. Therefore, this is the answer. And you can type this in the calculator and you will get the same answer. All right, so now down here, 25, 26, and 27, they are using the triangle that was constructed from the example above, so we do not have to create a new triangle, okay? But I am going to just draw it here so that we can zoom in. So we have root 89, and then we have our 5, and then I know that that's the length of a side, but I'm going to label it negative 8 because the coordinate point is negative 8. All right, so we have cotangent of arctangent of negative 8 over 5. Again, the output, this is equal to an angle. And based on my triangle, this is where my angle is. These are the same, okay? So based on the information that I got from the input for my arctangent, I was able to construct a triangle as it relates to that angle. So now that I have the 3 sides, I can evaluate cotangent for that angle. And we will use the same triangle because we are restricted to that particular triangle. So I'm essentially evaluating cotangent of theta, all right? All of this is theta. Do we know theta? No, we don't need to because we have the triangle specific to that theta. So cotangent theta, if I think of tangent, it's going to be opposite over adjacent. Cotangent is 1 over tan. So it's going to be the reciprocal, which means I can flip it. So I end up with opposite over adjacent. Opposite of my theta is the -8. The adjacent side is 5. So we have -8 over 5. And I was just thinking, tangent is positive in quadrants 1 and 4, and it's negative in, 1 and 3, and it's negative in 2 and 4, which means cotangent will share the same positivity and negativity. Because we are in quadrant 4, it should be negative, so I was just double checking that. Now for this one, again, this is equal to theta. And we have our same triangle that we had up above. So we're in quadrant 4, this was 5, -8, and then this is root 89. So now we're looking for secant theta. And this is similar to cosine theta. It's the reciprocal of cosine. So cosine is adjacent over hypotenuse, it's the ca, which means secant is going to be the reciprocal. So we will have adjacent, that was for cosine, so we'll have hypotenuse over adjacent. The hypotenuse for this triangle is root 89, and then the adjacent side is 5, which makes sense because cosine is the x values, all right? So anything in the positive direction horizontally means that cosine is positive. And then anything to the left means that it will be negative. So secant shares the same positivity and negativity. And since we are in quadrant 4, secant should be positive. All right, so now we have cosecant of arctangent of -8 over 5. So if I look at this one, again, this is theta. All of this is equal to a theta. And if I think of my right triangle in quadrant 4, we have the same one. So it'll be 5, -8, root 89. So now for this one, we are solving for cosecant theta. Cosecant is the reciprocal of sine. And sine is the y-coordinate. Or in this case, we can just think of SOHCAHTOA. So sine will be opposite over hypotenuse. Because cosecant is the reciprocal of sine, we can flip that ratio. So we end up with hypotenuse over the opposite side. The hypotenuse is root 89. And the opposite side is -8. So we end up with a negative ratio, root 89 on top, 8 in the denominator. And if we think about it, going down, sine is y, which means our y values will be negative for quadrants 3 and 4. And vertically, as we go up past the x-axis, your y values will be positive. And for sine, because cosecant is the reciprocal, again, they share the same quadrants. We're in quadrant 4, so it should be negative. And basically, if you rely on the sides that are negative, that will help you remember whether the ratio is positive or negative. So now these next ones, we might have to construct our own triangle because we can see that the input is different, all right? So we have cosecant of arc cosine of -1/2. Okay, so you only need to draw a triangle if it's completely necessary. This should jump out at you because it is a coordinate on the unit circle, all right? But which coordinate is it? So this is an inverse trig, which means the output will eventually be an angle or a theta. But think about, what is this coordinate? We're dealing with arc cosine, which means we are dealing with the x-coordinate as the input. So remember, we are working our way from the outside to the inside. With non-inverse trig, we have an angle, and then we expand out to find that coordinate. With inverse trig, we have a coordinate, and then we work our way in to find the angle, okay? So this coordinate is -1/2 for arc cosine. Arc cosine exists in quadrants 1 and 2. So that means we only have one option for -1/2. It's going to be in this direction, but it's going to be a little bit smaller. So it's going to be closer to the y-axis, which means that theta is equal to 2 pi over 3. So that means all of this is equal to 2 pi over 3. So we found the x-coordinate, and then we worked our way in to find the theta. So this is going to be equal to cosecant of 2 pi over 3. So there's a couple ways to solve this one. What you can do is you can go off to the side, and you can think of sine of 2 pi over 3, because sine is the reciprocal of cosecant. If I think of sine of 2 pi over 3, that's going to give me √3 over 2. Now, cosecant is the reciprocal of sine, and sine is the reciprocal of cosecant. So that means I can take this and I can flip it, and it will become the ratio for cosecant, which is 2 over √3. Something else that you can do, but it creates, there's more flipping to do. You could rewrite it as 1 over sine of 2 pi over 3. These two are equivalent. We didn't actually flip it to use the reciprocal. We're just rewriting cosecant. Since sine is in the bottom, it's still considered cosecant. So sine of 2 pi over 3 is √3 over 2. And then because we have the ratio on the denominator, we can multiply it, the reciprocal, with the numerator, which is 1. So we end up with 2 over √3. So both of these methods work. I mean, just pick the one that makes more sense to you, and then practice it consistently. All right, so for 28, we have cosine arctan of 4/3. So 4/3 you should recognize is not on the unit circle. All right, it is not a standard coordinate, so not standard coordinate, which means you will have to use a triangle. And yes, you can plug these in, but these should always be exact answers. So you will be constructing a triangle. So still focus on the fact that this is a theta. And what happens when it's not a standard coordinate on the unit circle, it's said to set the inner expression equal to theta, okay? So what that means is we have arctan, which means we will set that equal to theta. So we have arctan of 4/3 is equal to theta. Now I want to construct a triangle, so I want to use tangent. So I'm going to apply tangent. So I end up with tan theta is equal to 4/3. Now tangent is going to be opposite over adjacent. Okay, so we know two sides for the triangle. We know the opposite side and we know the adjacent side. Now, arctan only exists in two quadrants, 1 and 4. And because this is positive, it will be in quadrant 1, it being the triangle. So if I have my theta, my opposite side is 4, my adjacent side is 3. And then this is a special triangle. It is a 3, 4, 5 triangle. Now, if you don't remember that, it's not the end of the world. Just use Pythagorean theorem, and then you'll end up with 5 as your hypotenuse. I'll do that for the next one. I'm not going to do it for this one, though. So now that we have all three sides for our triangle, you are done with the inner function, okay? We were able to figure out what the relationship that theta has with this triangle. So now we will work our way out. So we end up with cosine theta is equal to, well, cosine is going to be adjacent over hypotenuse. The adjacent side is 3, the hypotenuse is 5. So we get 3/5 for this one. Now we have tangent of inverse cosine of 3/8. 3/8 cannot be evaluated. So we're going to use a triangle, okay? So again, all of this is equal to theta. The output is a theta. So I'm going to set it equal to theta. So inverse cosine of 3/8 is equal to theta. And then I want to rewrite this as a non-inverse trig. So I'm going to end up with cosine theta is equal to 3/8. So for cosine, this is going to be equal to adjacent over hypotenuse. So 3 is the adjacent side, 8 is the hypotenuse for our triangle. Inverse cosine exists in 2 quadrants, 1 and 2. This is positive, so this is going to be in quadrant 1 because the x values are positive in quadrant 1. So adjacent is 3, hypotenuse is 8. If this is a special triangle, I don't know, so I'm going to use Pythagorean theorem in order to get it. So adjacent is 3. I don't know the opposite side, and then this is, whoops, that should be equals 8 squared. So let's see, I get 9 plus b squared is equal to 64. B squared is equal to 55, which means b is equal to the square root of 55. And then make sure you use exact. Don't use that approximated decimal. We want to be as exact as possible. So now that I have my 3 sides for my theta, I'm done. I'm finished with the input, and now I'm going to work my way out. So with this particular triangle, I want to know, okay, what is tangent theta? Well, tangent theta is going to be opposite over adjacent, and the opposite side is root 55, and then the adjacent side is 3. So I can check this, okay? Let me see if I can pull up, and then I'm going to open this because I need that. So I have tan inverse cosine of 3/8. Let me see if I can find it. Yep, it's still there. And then there's all these adds that I'm not sure why they started putting all those in, but clear that out. Okay, so let's see. What did we have again? I forgot it because of the adds. Tangent of inverse cosine of 3/8. Okay, so tangent second cosine of 3/8. So what I'm doing is I'm checking to see if my answer lines up with what I got using that triangle. So the decimal value is 2.472. So if I type in what I got root 55 divided by 3. I also got 2.472. So we are good. So that's just a quick way to check. Essentially, that root 55 over 3 is equal to tangent of inverse cosine of 3/8. All right, that is the end game. That's what we're trying to solve. All right, so again, be careful with those. You don't always have to construct a triangle, especially if it's a standard coordinate on the unit circle. However, if you ended up making a triangle, you would still get the same answer, but it's a waste of time because you want to be as efficient as possible. If you don't need a triangle, don't construct it. All right, this is find an algebraic expression for each of the following. And what makes this an algebraic expression is now we are dealing with a variable x, okay? And this presents a little issue, and then it also helps alleviate some issues. So going forward, it doesn't change what inverse trig represents. It represents a theta, an angle, okay? And the input is going to be the sides of a particular triangle relating to this theta. So if we think about sine, we have opposite over hypotenuse. However, I do not see a ratio in my argument. But if I think of 3, that's equal to 3 over 1. If I think of x, that's equal to x over 1. So if I have x plus 1, that is equal to x plus 1 over 1. So any value that is not in fraction form, it can be written as over 1, which is going to expose what your hypotenuse is. And that's what's happening here. So for this particular one, we have x plus 1, which it looks like it's the only thing in there, when in reality, our opposite side is x plus 1. Our hypotenuse is 1. So the end game is we want cosine theta. That's what we want, but we need to construct this triangle first. So if we set the inside equal to theta, I have inverse sine of x plus 1 is equal to theta. I'm going to take the sine of both sides. So I end up with x plus 1 is equal to sine theta. Well, x plus 1 over 1 is equal to sine theta, which will give us our opposite over hypotenuse. Now, for these algebraic expressions, they will always be in quadrant 1. Reason being that the variable x, whatever quadrant we end up in, it will adjust to match that quadrant. So we just start in quadrant 1 and then we don't do anything more with these algebraic expressions. However, it helps us solve for the values based on what that algebraic expression is. All right, so I have opposite, which is x plus 1. And then my hypotenuse is 1. So I need my adjacent side. So from here, we can use Pythagorean's theorem. A squared plus b squared equals c squared. I don't know the adjacent side. I know that b is x plus 1, and then c is just 1. So isolating a, we end up with 1 minus x plus 1 squared, which means a is equal to the square root of 1 minus x plus 2 squared. Where did the 2 come from? Sorry, x plus 1 squared. Now, this is not the same. You cannot do that, okay? You can only apply this rule to monomials. Right now, we have a binomial under our square root. As soon as you get a subtraction or an addition sign under that square root, you cannot just apply that property, okay? It'll have to stay this way. So my suggestion is do not reduce. Just leave it as is. So our adjacent side is the square root of 1 minus x plus 1 squared. So now that we have the 3 sides for our triangle, we'll work our way out to cosine. So cosine theta is equal to adjacent over hypotenuse, which is equal to the adjacent side is the square root of 1 minus x plus 1 squared all over 1, which the 1 isn't necessary, but I'd rather do it to stay consistent with the ratio for cosine. All right, 31, we have sine arcsecant of 3 over x minus 1. This one's a little more obvious because now we actually have a ratio. But what we've always been doing when we run into our reciprocals for inverse trig is we flip it back, all right? Cosine, sine, and tangent are a little bit more familiar. Therefore, we want to try and work with them as much as possible. So if I rewrite this, I get sine. I'm going to change this to arc cosine. But when I use the reciprocal, it's also going to reciprocate my input. So I end up with x minus 1 divided by 3. Now for cosine, we have adjacent over hypotenuse. So x minus 1 is the adjacent side. Therefore, 3 is our hypotenuse. All right, so if we take arc cosine, and this intermediate step isn't always necessary, but it does help as a reminder that the output for inverse trig is an angle. Now, if we take cosine of both sides, these two cosines cancel out, cosine and arc cosine. So we have x minus 1 divided by 3 is equal to cosine theta, which is how we can construct our triangle. So it's algebraic, so it's going to be in quadrant 1. The adjacent side is going to be x minus 1. The hypotenuse is going to be 3. Now the end game is sine theta, and sine needs opposite over hypotenuse. And we don't have the opposite side, so we're going to have to use Pythagorean's theorem. Now, to get the leg, this is a quick shortcut. To get the leg of a triangle, you take a square root. You'll take the hypotenuse squared, and then you'll subtract the other leg squared. That's the quick way. Whenever you're solving for a leg, you take the hypotenuse minus the other leg, and they're both squared. Now, whenever you're solving for the hypotenuse, you'll take leg 1 squared plus leg 2 squared. Whoops. And that's just a quick shortcut. If you don't remember that, that's fine. Just use Pythagorean's theorem. But that's a quick shortcut. All right. So we have 3 squared minus x minus 1 squared. So the square root. 3 squared. Yes, you can write 9 if you want. There's no need to expand this. It's actually better in this form. So leave as is. Now that we have our triangle, we can work our way out to sine theta. For sine, we want opposite over hypotenuse. Opposite side is the square root. 3 squared minus x minus 1 squared all over 3. And the last one, we have sine of arctangent of 5 over x. With that x, I can see that this is going to be an algebraic expression, and we actually have one of the original trig expressions. So if we think of tangent on the unit circle, this might be a little confusing because we have the x in there, but luckily it aligns pretty well. So if we think about arctangent of 5x, that's already telling us two sides of our triangle, specifically the two legs, because we have opposite over adjacent. So what's the end game? We want sine theta. That's the answer. But we need a theta. We need to construct a triangle for this particular theta, which is what we will get from here. So if I have arctan of 5 over x, that is equal to a theta. If I take the tangent of both sides, I end up with tan theta is equal to 5 over x. You do not have to show this step. Hopefully, as you get more comfortable with these, you can see that the sides of your triangle are already the input for your inverse trig. Which means this is going to be opposite over adjacent. So it's an algebraic expression, so we'll be in quadrant 1. The opposite side is 5, adjacent side is x. So if I go back to what I talked about in the previous problem, if I want the hypotenuse, I'm going to take the square root, and then I'm going to square both legs and add them together. And this will give you the hypotenuse. And you can write 25 if you want to. So now that we have our full triangle, the end game is sine theta. Sine is equal to opposite over hypotenuse. The opposite side of theta is 5. The hypotenuse will be the square root of x squared plus 5 squared. All right, so that is compositions that involve inverse trig functions. Hope this helps.